Good evening, everyone. I'm Shivani, and I welcome you all for the week 11 tutorial for the course of Simulations of Communication System using MATLAB. So, like every week, this week's tutorial will also be divided into two parts. The first part will be simple recap of week 11 content, followed by questions which are related to the recap which are related to the content that was covered in week 11. If you have any questions, then you can stop me at any point. Kindly unmute yourself and then ask your questions as I'm not able to see the chat box. Okay, let's quickly start with the recap of week 11 content. So this week's content was in continuation with whatever we covered in week 10. So in week 10, basically we started with digital communication and we looked at different constellation schemes and their performance analysis. And we continue to do so in week 11, and we also looked at some more schemes for transmission and the ways we can detect them. But initially, in order to analyze or not analyze, in order to visualize the probability of error plots in a better way, what we have or what we conventionally do is we analyze or we consider the signal to noise ratio. So your SNR your SNR, which is, let's say, proportional to your ES by N naught. This is right now in a linear scale. To visualize the probability of error plot in a better way, what we do is we consider decibel scale, or what we call as dB scale. Okay, and to do so, what we do is this SNR in dB scale is simply equal to 10 log SNR to the base 10. So this is the uh, conversion formula, and we can get this linear one. Okay, to just demarcate it properly, let me just do it in this way. So the linear scale, the SNR from dB can be obtained by simply 10 to the power SNR dB by 10. Okay, this is the simple thing that we consider. After that, we looked at what is known as multi-dimension signal. But to first understand what these multi-dimensional signals are, let us first understand what is the dimension of a signal space. So we have seen, you can write this xt as summation n equal to 1 to capital N xn phi n of t, where this phi n of t for n equal to 1 to capital N is a set of bases. Okay, now we are writing this signal x of t as a linear combination or weighted combination of this basis signals. And how many number of bases do we have? Or so number of signals in the basis set is equal to n, and this n is known as the dimension of this signal space, which is spanned by this, or which is defined by this set of bases. So n is the dimension of signal space spanned by these bases. Okay, so What do we mean by multidimensional signals? So multidimensional signals mean, before going to multidimensional signals, let us first understand what the bases are. And this is equivalent to the vector representation also. So if I have a set, this set, then this is basically two-dimensional. These two are linearly independent, and these are orthogonal also. Then if I consider this 0, 1, 1, 0, and 1, 1, this is also two-dimensional. Why? Because I can write this 1, 1 as 0, 1 plus 1 times 1, 0. Okay. Then another example of three-dimensional signal is this. Here dimension is 3. And similarly, if I consider this set, this is again two-dimensional. And why? Because we can write this 0, 1, 1 as 1 into 0, 0, 1 plus 1 into 0, 1, 0. Okay. Okay. Now we looked at this class of multidimensional signal. So it says that the constellation has n greater than or equal to 2. So it is having more. And to understand or an example, or let's say what we considered is for an m point constellation, dimension is m, and example of such a constellation is orthogonal signaling. So for example, for m equal to 2, the constellation of 0 under root es, then under root es 0. So this is two-dimensional orthogonal signaling. Then if I have m equal to 3, then it is 0, 0 root es, 0 root es, 0, and root es, 0, 0. Okay, so this is all. We also saw how the probability of error trends are. I won't go into detail of this, but we'll see how the detection rule for this particular scheme goes ahead when we have introduction of phase and scaling factors. Okay, so this we have here. After that, we looked at an important concept of coherent and non-coherent detection. So what do you mean by coherent detection? Basically is when we are transmitting some information through any channel, any physical channel. So when we transmit signal over any physical channel, the signal gets one attenuated, or in other words, we'll write it in this fashion. The signal gets, or the signal amplitude is affected, phase is changed. This phase is changed due to propagation delay. Third thing, AWGN gets added. So what happens is, if I'm transmitting xn, or x is symbol which is transmitted, then received signal is y equal to some g attenuation factor e power j theta, where theta is the phase, x plus w. So this g is attenuation factor and this theta is phase, and these both are random. And we know that this W is AWGN, additive white Gaussian noise. Okay, now what happens is, so we have this signal y equal to g e power j theta x plus n. Now this is rotating and scaling the signal entirely, right? So this is affecting my signal, affecting everything. So what we do is, so if I know, so if we know g e power j theta, then we can reverse the effect, or the effect, rotation and scaling by it. Of course it will affect the noise part, but still we can simply multiply by let's say multiplying by e power minus j theta into g power minus 1. And if we do that, we can simply revert. However, the noise factor will get affected, the SNR will change, that's okay, but we'll have y equal to some noise term. Then we can simply apply whatever rules we have done till now. So whatever approach we have seen till now, so till last week, we have seen this will allow coherent detection. Now suppose we don't know this theta and g. We cannot predict or see, or we cannot interpret how g and theta have affected the received signal. And what does this mean? And we don't know anything about it, which means our decision rule should be such that it is least affected by g and theta, and such kind of rules, such detection or decision rules are non-coherent detection rules. Okay, and two examples we saw, or two cases we saw for non-coherent detection. First one was orthogonal signaling. We have seen it. So it simply means that m point constellation has m dimensional signal, and each signal is orthogonal to each other. So this orthogonality can be brought in time, it can be brought in frequency as well. When we do it in frequency, that kind of constellation or that kind of modulation technique is known as frequency shift keying. And same thing we can repeat in time as well. And another approach that we looked at was this DPSK, where this DPSK stands for differential phase shift keying. That is DPSK. Okay, so we have this thing here, and what does this DPSK do? So the modulated signal, so what happens is we have a sequence of 1 and -1 going into DPSK modulator. It gives another sequence of A plus minus A. Okay, so this is output sequence. So output sequence phase is changed if there is a change in phase of input. So what am I trying to say is, for example, so let me just take it here. So for example, if my input is -1, 1, 1, -1, -1, -1, then output is, we have a reference. So this is initial reference. Then since I have a -1 here, I have a phase change. So this will be -a. So here to here, I'll have a change of phase of pi. Then from -1, it is going to 1. So again, there is a phase change. So here also I'll have a phase change. So again, pi radian phase change. Now I have 1 to 1. So that will remain a. Again, I have -1. So that will be no phase change. Now here it is -1. Same, nothing is changing. So it will remain as it is, as it is. Okay, so this is known as differential phase shift K. Okay. Any questions? If you have any questions, then let me know. Otherwise, I'll move on to the next question. Okay, if there are no questions, then so just a minute. I have a small mistake here. Yeah, so I made a mistake while discussing this DPSK. I'm sorry. So you will have 0, 1 coming here in the input. This is DPSK, and this will give you plus minus a. So what will happen is, you will change phase whenever input bit is 1. So for example, if my input bit binary string is 0, 1, 1, 0, 0, 1, 1, 1, 0, then let's say my initial reference is a, then this is 0, nothing will change. Now I have I have a 1, so I'll change a phase. Then I again have 1, so again I'll change the phase. Now it is 0, it will remain as it is. Again it is 0 as it is. Now I have a 1, so it will change its phase as -1. Then again 1, so it will change its phase. Then again 1, again it will change its phase. Now it is 0, it will remain as it is. Yeah, extremely sorry for the confusion, but this is the signal. So what is happening is, From 0 to 1 it is having a transition, so pi radian phase shift. Then again we have 1 to 1 here, so from here to here again I have a pi radian phase shift, but now I have a 0, so there is no phase shift. Now again it is 0, so no phase shift. Then I have 0 to 1, so again a phase shift, then again a phase shift as I have a 1, then again a phase shift as I have a 1, and this is sorry, this will be minus, yeah. uh, Again it is a 0, so no phase shift, so it will remain as it is. So this indicates change of phase. We saw how to decode this as well. I won't go into its details. If you have any questions, then please let me know. Otherwise, I'll move on to the questions that I have planned to cover today. Okay, so let's move on to the questions that I have planned to cover today. So let's start with the first question. So like every week, these week's questions will be a mix of the questions that were covered in last year's assignment, as well as some questions which are covered, which I have uh, taken from some reference or from some other good reference. Okay. So let's start with the first question. This is a last year assignment question. So it says that coherent detection offers a dash symbol error rate for the same transmitted symbol power as compared to non-coherent detection. We have seen what a coherent detection is. It means you know the knowledge of your G and theta. And for non-coherent detection, you don't know the value of your G and theta. Your constellation is already messed up. Which means that if I know some knowledge of my G and theta, somehow a little bit better I can do. So therefore, this coherent detection offers a lower probability of error or lower symbol error probability. So this coherent detection has lower probability of error or lower SCP or SCR, let's say, this is your SCR, that is symbol error rate, lower SCR than your non-coherent detection. And why is it so? This is because in coherent detection, we know G and theta, which allows us to have better detection. And leads to slightly lower SCR. Is it clear? Any question? Okay, if there are no questions, then let me move on to the second question. So the second question says that, this is also last year assignment question. So it says that coherent detection does not require phase information for detecting the received symbols. No. So we said that this coherent detection requires G and theta, which means that it requires the knowledge of this phase, that is theta. So this is a false statement. So coherent detection requires the knowledge of, or requires the phase information. What is it doing essentially? Let us try to understand. Okay. So let's say I have a BPSK constellation. Okay. So same constellation I have like this. So what I'm doing is I'm transmitting minus root es. So let's say 0 and root es. So you have here your minus root es, 0, root es, like this. And this thing is transmitted over a channel, and the channel introduces propagation delay. So this will get multiplied by g into e power j theta. So what does it mean? This theta is an angle. Just e power j theta implies that there is some sort of rotation. So this factor here is simply rotating the constellation by angle theta, and this factor here is scaling the constellation. Okay, so what is happening now is this constellation here now gets rotated by an angle theta, something like this. So this angle is theta, and along with that it gets multiplied by this factor g. So then we have some sort of scaling also. Let's say g is less than 1, between 0 and 1. So this thing here will be simply g e power j theta root es, and this point here will be equal to minus g e power j theta root es. So this is what is happening. And what does coherent detection do? So this coherent detection will undo. So let me just take this part here. Okay, so we have this. So what we have is this one here. This one here, it was my transmitted constellation. What do I mean by transmitted constellation? One point of these two was transmitted, and this one here is what I have received constellation. So now if I multiply by e power minus j theta, that is I undo this rotation, this phase rotation. So I may again bring it back down here. What will I get? I'll get something like this. I'm just multiplying it by e power minus j theta. Okay. So earlier I had this thing. I had this minus root es and root es. These are my original constellation. Now what will I get? Instead of these, I will get these points. And what are these points? These are basically g root es, or g into minus root es, and g into under root es. So this is post multiplying by e power minus j theta, and these two are your original points. Now so this is undoing the phase rotation. So here we are undoing phase rotation. And now if I multiply, so this is okay. Now I have a constellation which is of the same format. I'm happy. It's okay. With this also I can go ahead and do detection rules. Just the comparison point will be different. Along with that, if I divide it by g, then what will I get? I'll get back my original constellation. Yeah, this is, I'm completely ignoring the noise right now, but this is what we'll get. So this will give me, so this is undoing scaling. So if I just have the knowledge of phase, this is what I get, and still I can do something. I'm at a better position. But now if I also know the amplitude, I can do something more, and this is what I can do more. Of course, the noise will also get scale, but it's okay. For now, this much is. So this is how coherent detection will help me. It will bring back me to the original constellation which I intended to transmit. It helps, or it allows me to use the existing detection approaches. Is it clear? Any questions till this point? So therefore, for coherent detection, this requires the phase information. In order to do this part, I need the phase rotate. So for this particular part, for doing this, we need to know theta. Okay, is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. So the next question says differential phase shift keying uses the phase difference between the subsequent transmitted symbols to transmit modulated data. So this is true. So it looks at the phase difference between the subsequent transmitted symbols and then does the thing. And however, So this is by principle of DPSK. We have seen some example earlier. We'll see some more examples in the coming questions. But this is by the definition or by the nature or by construction. This is how the DPSK works. Any questions? Okay, if there are no questions, then let me move on to the next question then. So the next question says all non-coherent signaling schemes can be detected coherently. So I can apply this coherent detection algorithms. If I know the theta and z, I can go for coherent detection algorithms irrespective of the scheme that I am using. So even if I'm having orthogonal signaling, I can derive a detection rule for coherent detection. We'll see if the time permits, we'll see how to do that. So this statement is true. However, if I have a coherent detection scheme, or if I have a coherent detection scheme only, which can't be done using which definitely requires me to know the phase information at least, then in that situation I can't use non-coherent detection algorithms to do the same. A simple example is the phase shift keying, which we'll see in one of the questions. So, or in simple words, if any constellation scheme, if it has some information, or if it has its information embedded in its phase, then in such a situation, if my phase only is affected by the scaling thing, then I can't go for a non-coherent detection because my constellation is badly changed and I can't detect it. I can't understand what is happening. So I can't use non-coherent detection approaches to detect the coherent detection scheme. Is it clear? Okay, if it is clear, then let me move on to the next question. Okay, so here I'll just modify this a little bit. Instead of doing -1, I'll take it as 0. Okay, so what is given is, for the given binary string, obtain the output for DPSK scheme and assume the initial voltage level as A. So let's say this is the first one, this is second one, and this is third one. So what is the first one? So the first one is 0, 1, 1, 1, 1. 0, 1, 0, 1, 0, 1, 0, 1, and 1. So let me write it again. So it is 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay, and initial voltage level is A. Now I have, so let me just bifurcate. This is my initial voltage level, which is A. I am seeing a 0. So if I see a 0, nothing will change. I'll be at the same state. If I see a 1, I'll change the phase, that it will become minus A. Now, if I again see a 1, I'll change the phase. If I see a 0, I won't change the phase. I see a 1, so I'll change the phase again back to A. Now again I am seeing a 1, so I'll change the phase. Now again I am seeing a 1, A. Now I'm seeing a 0, so it will remain as it is. Then I'm seeing a 1, I'll have a phase change. I'm seeing a 0, it will remain as it is. Then I see a 1, I'll change the phase. I see a 0, I'll keep it as it is. I see a 1, I'll change the phase. Again I see a 1, I'll change the phase to minus A. So this is for the first one. Is it clear? Any questions at this point? Okay, if there are no questions, then I'll move on to the second part. The second part is simply 0, 0, 0, 0, 0, 0, 0. So 7 times 0. 1, 2, 3, 4, 5, 6, 7. Okay. So again, initial voltage level is A. Now I am seeing a 0, so it will remain as it is, nothing will change. Then again I see a 0, nothing will change. Again I have a 0, no phase change. I have a 0, no phase change. Same, again 0, no phase change. Again 0, no phase change. Again 0, no phase change. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the third part. Third one is 7 times 1, like this, and initial one is, or initial voltage level is A. So if initial voltage level is A and I'm seeing a 1, I will change the phase as minus A. Now again I am seeing a 1. So if I'm seeing a 1, I'll change the phase, I'll make it A. Again I am seeing a 1, it will change as minus A. Then I again see a 1, I'll make it as A. I see a 1, I'll again change the phase to minus A. I see a 1, I have A here. Then I see a 1, I'll have a minus A. Is it clear? Any questions till this point? Is it clear? Any questions? Okay, if there are no further questions, I'll move on to the next part then. So this says that in the previous question, comment on how the phase of the carrier varies post modulation. So in order to do that, I'll just copy paste these on the next page. Okay, so this is the thing that we have. Okay, so this was my input, this is output, this was input, this is output, this is input, this was output, and now what we will see is phase change. Let's start with the first part. So in the first part, what we had was, yeah, okay, so first we had a 0 and initial voltage level was A, and since we saw 0, there was no phase change, so it was 0 phase change. Then we saw a 1, then there was a pi radian phase change. Then again we saw a 1, then again we had a pi radian phase change. After that, we again saw a 1, again we have a pi radian phase change. We get a minus A after A. And after that, again we had a 1, so again we will have a phase change. So we have this minus A getting converted to A. Okay, but after this 1, we observed a 0, which means that whatever was the phase, whatever thing we had, there shouldn't be any phase change. So now we have no phase change. But after the 0, again we had this. So after the 0, again we had this 1, which means again we'll introduce a phase change here. Again from 1 to 0 we are going. Since we saw a 0, no phase change. Minus A remains as minus A. Then from 0 to 1 we have a phase change. Then again from 1 to 0, since we observe a 0, there won't be any phase change, so A will remain as A. From 0 to 1, since we saw a 1, we'll have a phase change, and again after 1 we have another 1, so therefore we will have again a phase change. Any questions? Okay, let's repeat the same exercise for the second part now. So here the initial state was A, then we saw a 0. Since it was a 0, no phase change. After that we saw a 0 again, so again no phase change. Then again we saw a 0, again no phase change. We saw another 0, no phase change, and 0, no phase change. Again we saw a 0, no phase change, and again last one was also 0, so again no phase change. So since I saw a series of 0, there is no phase change. Now we have 1. My initial state was this A. Since I saw a 1, there is a pi radian phase change. Again I saw a 1, again I'll have a pi radian phase change. Again I saw a 1, again pi radian phase change. 1, pi radian phase change. Again I have a pi radian phase change. Then I have 1 again, so again pi radian phase change. Again I see a 1, again pi radian phase change. So whenever I see 1, I'll change the phase by pi radians. Is it clear? Any questions? Okay, if there are no further questions, let me move on to the next question then. Okay, so this question is, in a binary data transmission, DPSK is preferred than PSK because a coherent carrier is not required to be generated. Option 2 is, for a given energy per bit, the probability of error is less. No, we have seen this. This is not the correct option. Then, 180-degree phase shifts of carriers are unimportant. No. More protection is provided against impulse noise. No. So the correct option is, a coherent carrier is not required to be generated. Why is coherent carrier generation important for PSK? Let us try to understand that. How does the PSK constellation look? So PSK constellation basically, or the points of the PSK constellation basically lie on a circle of radius, let's say some root S. So the constellation points lie somewhere like this. Okay. So this is your constellation point. Now if I multiply it, or if I have g into e power j theta, something like this, what will happen is, this entire constellation yeah, so I have this constellation here. So what will happen is, this constellation we have something like this, and this was 0 angle. So now the things will get changed a bit. So this first point will be at this angle theta, and this will be of radius g root es. So my first point will be here. Here. Then my second point will be somewhere here. So one point will be here. One point will be here. 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 Somewhere here. 1, 2, 3, 4. Sorry, 1 second. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. One point will be somewhere here. Okay. Yeah, something like this will happen. So all of these points are shifted little bit by um, an angle theta. But all the information all the information is in the phase of constellation points. So what is happening is, multiplication by g into e power j theta in a PSK constellation directly affects the phase of every constellation point and hence affects the information. So therefore, if we don't have any knowledge of theta, we cannot retrieve any piece or any information to any level of accuracy. So my phase information was in the phase by multiplication or by introduction of this random phase component of e power j theta. My entire information is lost. Therefore, for PSK, we need to know theta so that we can undo the phase rotation that was introduced by theta. What it means is PSK we cannot do non-coherent detection. And not only PSK, in general, for any constellation where the information is in the phase of the constellation we cannot use non-coherent detection. We need the knowledge of theta to obtain or to coherently detect the received signal. Is it clear? Is it clear? Any questions? Okay, if there are no questions, then let me quickly move on to the next question. So next question says that derive the ML detection rule for m equal to 2 orthogonal signal. So what does it mean? So for m equal to 2 orthogonal signaling, following constellation is transmitted. So let's say this is my S1 and this is my S2. Okay. So what I will receive and what we will consider is each dimension so this is my dimension 1 and dimension 2 is affected by a complex number Gi, where I belongs to 1 or 2 and I implies dimension. Okay. And Gi are IID random variables distributed as Cn 0 comma sigma g square. Okay, these are the assumptions that we are having. And another thing that we will consider is let each dimension be affected by noise or IID noise Wi, which is distributed again Cn 0 comma n naught. What does Cn mean? Cn means circularly symmetric complex Gaussian. Okay, so we have these two things and we have the noise Wi, like that is W1 and W2. So for different transmissions, that is for transmitting S1 and for transmitting S2, I'll receive two different kind of signals. So what will happen is, so if S1 is transmitted, what I will get is, I will get two components. So for dimension 1, I will get, or let's say, in order to be very precise, what we will do is, let vector y be equal to y1, y2 be the received signal. Okay, so now this y1 and y2 will change based on what we have transmitted. So first thing is, if s1 equal to, what was my s1? 0a is transmitted, then I have y1 equal to, so we have this g1 into 0 plus w1, which is equal to w1, and my y2 will be equal to g2a plus w2. Okay, now let us first understand the statistics of these. So this y1 is equal to w1, so therefore this is distributed again as cn 0 comma n naught. Okay, and this thing here, this g2 is also cn 0 comma, so this g2 is cn 0 comma sigma g square, which means this entire thing here is simply cn 0 comma a square sigma g square. Now this is a Gaussian random variable, so Gaussian, this is also cn, this is also cn, so addition of these two will lead to another circular symmetric complex Gaussian. So this will also be cn, means will get added 0, and the variances will also get added because your g2 and w2 are independent. So this will be sigma g square a square plus n naught. Okay, and this y1 and y2 are independent. Okay, now so this is for the case when S1 is transmitted. And okay, let us do one more step. What we'll do is we'll write the joint density of y1, y2 given S1 is transmitted. So that will be equal to PDF of this quantity multiplied by PDF of this quantity, because both of them are independent. So what is PDF of y1? That will be equal to 1 upon pi n naught into e power minus magnitude of y1 square by n naught multiplied by 1 over pi into a square sigma g square plus n naught into e power minus magnitude of y2 square upon a square sigma g square plus n naught. And this is inside like this. Okay, now second part, suppose S2 equal to A0 is transmitted. So in that situation, y1 will be equal to ag1 plus w1, and y2 will be equal to 0g2 plus w2, which is equal to w2. Now like the previous case, this thing will be distributed cn 0 comma a square sigma g square plus n naught, and this thing will be distributed cn 0 comma n naught. Now again we can write the PDF f of y1 y2 given s2, that will be equal to PDF of y1 multiplied by PDF of y2, so that will be equal to 1 upon pi a square sigma g square plus n naught multiplied by e power minus y1 square divided by a square sigma g square plus n naught whole multiplied by the PDF of y2, so that will be equal to 1 over pi n naught into e power minus y2 square by n naught. Okay, Now, what is the decision rule? Decision rule is ML rule. So ML rule will be we'll decide in favor of that symbol which will have the highest likelihood function. So if of y1 y2 given s1 being transmitted, if this is greater than your f of y1 y2 given your s2 being transmitted, then we will decide in favor of s1. Otherwise we will decide in favor of your s2. Okay, so let us try to solve this part then. What is f of y1 comma y2 given s1? S1 is this factor here, so this is equal to 1 over pi n naught into e power minus y1 square by n naught multiplied by 1 over pi n naught plus sigma g square a square into e power minus mod y2 square divided by n naught plus sigma g square a square. One over pi n naught e power minus y2 square by n naught into 1 over pi n naught plus sigma g square a square e power minus magnitude of y1 square divided by n naught plus sigma g square a square. Okay, we can cancel out the common terms. These are the common terms, and we can take log on both the sides. So taking log, natural log on both sides, what we get is something like this. So we have magnitude of y1 square by n naught minus magnitude of y2 square by n naught plus sigma g square a square. And similarly on the right hand side we'll have magnitude of y2 square by n naught minus magnitude of y1 square divided by n naught plus sigma g square a square. Now what we will do is we'll take y1, everything that is a function of y1 square on right hand on left hand side, and everything that is a function of y2 square on the left hand side. So what we'll do is we'll take this here and we'll shift this side. So what we get is magnitude of y2 square, then we'll have this 1 over n naught minus 1 over n naught plus sigma g square a square. If this is greater, then I have s1. If it is less, then I have s2. Magnitude of y1 square inside the bracket again 1 over n naught, same term, minus 1 over n naught plus sigma g square a square. Let us simplify this term. These are common terms on both the sides, but just to understand what the sign of this term is, we have y2 square, then we will have n naught plus sigma g square a square minus n naught upon n naught plus sigma g square a square. So we have this n naught getting cancelled, then we have this s1 s2, then we have magnitude y1 square, then we will have same term here sigma g square a square divided by n naught into n naught plus sigma g square a square. If you observe carefully, both of these terms are same and both of these terms are positive. So if I cancel these two from both the sides, nothing will happen. The inequality will remain same. So if I have y2 square greater than y1 square, then I'll decide in favor of s1, and if it is less, then s2. So what was my s1? My s1 was 0a, and what was my s2? My s2 was a0. So this will contribute to y2. and this will contribute to y1. So now if my y2 energy of y2 is higher than the y1, which means that there is something additional that is coming up in the second dimension, and therefore I'll decide in favor of S1. And similarly, if something is happening, or if y1 is higher than, or the energy in y1 is higher than y2, then something additional is there in the first dimension, and therefore I'll decide in favor of y1, sorry, in favor of S2. And this particular rule here is known as energy detector. This we have seen in the lecture. However, how we arrived to this particular point was not discussed. Therefore, I purposely added this particular question. Is it clear? Any questions at this point? Okay. Okay, if there are no further questions, I'll move on to the next question. So now what it says is, generalize the result in question 6 for any m. Okay, so what I'll do is, I made a weird choice of S1 and S2 here. Like S1 I had the second dimension as A, and in S2 I had the first dimension of A. So what I'll do is, here for general M, what I'll do, so this mth point in constellation, so let the mth entry be non-zero, or mth entry be positive. Okay, so this is Sm that I'm having here. Okay, and this is the mth point in constellation. Okay, and this is mth point of m point orthogonal signaling. Okay, so now again same thing we will have. Let's have this noise vector as w1, w2 and so on till wm, and this wi be again cn 0 comma n naught iid, and let's have this g1, g2 and so on till gm, again cn 0 comma sigma g square iid scaling. Okay, so what will happen is, so when Sm is transmitted, what I will receive, my y1 will be g1 into 0 plus w1, which is w1, y2 equal to g2 into 0 plus w2, which is again w2, and so on. Then I'll have this y little m equal to gm a plus wm, and so on. We'll have this ym as gm, sorry, yeah, gm into 0 plus wm, which is equal to wm. Same way, same whatever we did for 2, now we are replicating the same thing for any general m. Okay. So again, this will be distributed Cn 0, n naught. This will be distributed again Cn 0, n naught. So on. This will be distributed Cn 0, n naught plus a square sigma g square. So on. This will be distributed again Cn 0, n naught. And since all these gi's are independent and these wi's are independent, these are a bunch of independent random variables. Okay, which means I can write f of y1, y2 and so on till ym given Sm being transmitted as product of I equal to 1 to m f of yi given Sm. Okay, then I can productify this. I can simplify this further as I can separate out. So if you observe here, y1, y2 till ym, except for this little m, are distributed identically and independently. So what I can do is I can simply separate out this factor, that is f of ym, y little m given Sm, multiplied by product of I equal to 1 to capital M, where I is not equal to m, f of yi given Sm. Now this factor here is equal to 1 upon pi n naught e power minus magnitude of yi square by n naught. And this is happening how many times? This is happening m minus 1 times. And this factor here is equal to 1 over pi n naught plus a square sigma g square into e power minus ym square divided by n naught plus a square sigma g square. Okay, so we have this now. So what we get is, therefore, f of y1, y2, or in other words, I can write it simply f of y given Sm. So I can write this to be equal to f of y given Sm, since this y1, y2 and so on till ym constitute a vector. So, okay, just write it. Y is this vector y1, y2 and so on till ym, like this, and this will be equal to one over pi n naught plus a square sigma g square into e power minus ym square divided by n naught plus sigma g square a square multiplied by 1 over pi n naught to the power m minus 1 into e power minus summation I equal to 1 to m for I not equal to m magnitude of yi square by n naught. Okay, so I have this. Let's simplify this a little bit. What I can do is, this particular summation that I have here, I can write it as summation I equal to 1 to m magnitude of yi square by n naught minus, I am ignoring this minus sign, this is outside only, this minus magnitude of ym square by n naught. And if I do that and if I further simplify it, what I get is this will be equal to 1 over pi to the power m and naught to the power m minus n. So I have taken this pi common, then I have this n naught to the power m minus n into n naught plus a square sigma g square, and this quantity here, this thing here, I can write it equal to norm square by n naught. This is L2 norm, Euclidean norm. This is simply distance of y from vector y from origin. So then I have multiplied by e power minus norm y square by n naught into e power minus, so I have a minus sign here, that will become plus magnitude of ym square by n naught into e power minus ym square by n naught plus sigma g square a square. And this factor here I can further simplify as e power magnitude of ym square inside the bracket 1 over n naught minus 1 over n naught plus sigma g square a square. This becomes e power magnitude of ym square into simply sigma g square a square over n naught plus sigma g square a square. Okay, so therefore f of y given, so what I have now is f of y given Sm being transmitted is equal to 1 over pi to the power m and naught to the power m minus 1 and naught plus a square sigma g square multiplied by e power ym square sigma g square a square divided by n naught into n naught plus sigma g square a square minus norm of vector y square by n naught. And what is my ML decision rule? ML rule is decide in favor of m hat, which will give me maximum over m f of y given Sm. So this becomes argmax of m into 1 over pi to the power m and naught to the power m minus 1 into n naught plus sigma g square a square multiplied by e power sigma g square a square upon n naught into n naught plus sigma g square a square magnitude of ym square minus norm of y square divided by n naught. Okay, now this is a common term. This thing here is common. And positive, drop it. So we can drop it. Nothing will change. So this will get argmax of m, and again we can take log also. So what we will be left with be simply sigma g square a square upon n naught plus sigma g square a square magnitude of ym square minus y square by n naught. So this is some simple constant term which is added to all. It is not contributing anything to maximizing this particular argument. So this is common. Similarly, this factor here is also common for all. It is not a function of m. So we can simply drop. So what we are left with is, another thing is, this addition is not going to affect any maximizing the component. In similar fashion, the scaling here is positive quantity. So again, it won't affect my multiplication. Maximization. So this now is equivalent to having m hat equal to argmax of m, and this m belongs to 1, 2 and so on till capital M magnitude of yn square. So if I specialize my m to be equal to 2, I'll get back the original or the previous question answer. Is it clear? So again, this is also energy detector. And this energy detector is non-coherent. Detection scheme. Is it clear? Any question here? Okay, if there are no further questions, then let me do something more also, since we have 15 minutes of time. So in previous in one of the question that we did today, so what we said that we can use coherent detection schemes to detect the scheme that is for non-coherent detection. So what we will do is, we did non-coherent detection for this particular scheme. Now for the same scheme, we will apply coherent detection. So what we will do now is, we will use coherent detection scheme for the constellation, or for the, let's take it, m point orthogonal signaling constellation. Okay, so now same thing we have the same receive equation, nothing changes, same receive equations we will have. So I'll just copy paste them. Okay, this is what we will be receiving, nothing changes. What changes now is, since we have coherent detection, we know G1, G2 and so on till Gm. We know these. So now what will happen is, if I have the knowledge of these things, this thing, I'll take up this. So, and we know this. So now the decision rule will be m hat as argmax over m f of y given Sm was transmitted and g. So everything, since this will come up, this is because we know what g is. Okay. So now whatever we need to do is now based on given g. Okay. So now given g, this is again distributed Cn 0 comma n naught, since it is just w. Again this will be distributed 0 comma n naught. However, this mth will be distributed. So now I have the knowledge of g. So which means given g, this is a constant. This a is a constant. Given g, this particular thing is constant. And this is getting added to a complex Gaussian random variable, which means it will perturb the mean and the variance won't change. And therefore, this will now be equal to g distributed as Cn with mean gm comma a and variance n naught. And similarly, the last one again will be Cn 0 comma n naught. Okay. Now we want to apply this particular decision rule to this. And as I mentioned earlier, since the noise are independent from these GIs and everything, so these are independent. Okay. So therefore, this f of y given Sm being transmitted and g is equal to simply product of I equal to 1 to m f of yi given Sm being transmitted and gi, since gi is just affecting the ith component. So this I can write as, again I can split like the previous one. So ym given Sm and gm multiplied by product of I equal to 1 to m, I not equal to m, f of yi given Sm and gi. So now here this particular quantity will have PDF of, write it properly, this particular thing is equal to 1 over pi n naught into e power minus ym minus smgm square by n naught, so, sorry, agm. And these particular things here will be equal to 1 over pi n naught e power minus mod yi square by. Okay, so now what we get is, therefore f of y given Sm comma g comes out to be equal to, so we have this one pi n naught, and this pi n naught is m minus 1 times, so what we will get is pi n naught to the power m to e power minus ym minus agm square by n naught multiplied by e power minus summation I equal to 1 to m and not equal to little m mod yi square by n naught. Now again I can use the same trick as we did in the previous part, as 1 over pi n naught to the power m, or let me write it nicely. I can write, or I can take up this part and I can write it as summation I equal to 1 to m mod yi square by n naught minus ym square by n naught. So this becomes norm y square by n naught minus ym square by n naught. So now what I get is something like this. So therefore f of y given Sm comma g is 1 over pi n naught square e power. I'll combine these two, this one and ym component. So this will be equal to minus of ym minus agm square plus, sorry, plus minus ym square by n naught multiplied by e power minus norm y square by n naught. Okay, so therefore the decision rule is, therefore m hat equal to argmax of m belonging to 1, 2 and so on till capital M f of y given smg. So this becomes argmax over m, and I have this quantity here 1 over pi n naught to the power m into e power minus norm y square by n naught multiplied by e power minus magnitude of ym minus agm square plus magnitude ym square. So now again this part here is common and positive, which means drop directly without changing the max to min, and again we can take natural log. So what we are left with now is, so this will be equal to m hat will be equal to argmax of m minus magnitude of ym minus agm square plus magnitude of ym square by m naught. Again this is a positive quantity and common, we can just drop it. So what we have is argmax over m. We can simplify this further. So what we will get is minus magnitude of ym square minus 2a real part of gm ym conjugate plus a square magnitude of gm square plus magnitude of ym square. So this gets cancelled, and what we are left with is argmax. And I can also multiply and divide by 2. Let it be here. Yeah, just keep it as it is. So what we will have is 2a real part of gm ym conjugate plus a square magnitude of gm square. Okay, I can write it a little bit different. So I can just multiply it by half uniformly for all m, nothing will change. Sorry. So that will give me, and also a is common, I can take out a also. So what I'll get is real part of gm ym conjugate plus a magnitude of gm square by 2. So what I did from here to here, divide by 2a. Okay, since both 2a, so since 2a is greater than 0, nothing will change, and this is the final decision rule. Now an important thing to note here, this is a coherent detection rule. So let me write it again. So this m hat, which is equal to arg max of m real part of gm by m conjugate, or we can also write it as ym gm conjugate. Nothing changes since it is a real part, nothing changes. A times gm square by d. Okay, so this is what we are having here, and now what happens is this is what we get. So this particular rule here, whatever we have obtained, this is coherent detection rule. This is maximum likelihood ratio. So this is ML rule. Then this term, okay, I made a small mistake here. You'll have a minus sign. So this term here, this term here is known as energy compensation term. And this term here, or to be very precise, this part here is known as sufficient statistic or decision statistic. Is it clear? Any questions? If there are no questions, that's all I wanted to cover today. Thank you for attending today's session. If you have any questions, please let me know. Otherwise, you are free to leave the meeting. Thank you for attending today's session. Another thing is I will be taking a summary session which is scheduled on October 20. You will get a mail for that. But if you have any questions related to this course and doubts which you want me to cover in that summary session, please post them before 15th of October. So I'll take in the question answer portal of our course. So just put your questions there and I'll take up those questions in the summary session. That's all from my side for today. Thank you for attending today's session.